In this video, we will describe the process of a quicksort algorithm. So let's look at the exam question. Describe how a quicksort algorithm works with the data in a 1D array below. So this is the data of unsorted integers that we are going to sort. So first of all, let's look at the steps involved in a quicksort algorithm. Step 1. Set a pointer to the first value in the array, the value on the left. Set pointer B to the last element in the array, the element on the right. While these two pointers don't contain the same value, they are not equal, perform the following stages. A. If the data identified at those pointed positions within the array is in the wrong order, swap the data and swap the locations or the index positions that the pointers are currently looking at. And then you're only going to move pointer A value towards the value of the pointer B. When this loop is completed, you should find that pointer A and pointer B now have the same value. In other words, they are pointing to the same index position. You will then repeat the above process for the data sublist to the left of pointer A, and then you will repeat the same process to the sublist to the right of pointer A. Now that can be quite difficult to follow, so let's use a worked example to show how this works. So in our first row, we can see our data is unsorted. Notice how I have placed pointer A at the left and B on the right. And we simply compare the data that is being pointed to by A, which is the value 2, and the data being pointed to by B, which is the value 5. So we're going to sort this into an ascending order, so the 2 and the 5 are in the right position. We only move A towards the pointer B. We now compare the 1 and the 5. Those two pieces of data are in the right order. Move the A towards the B. Compare the 4 and the 5. They are in the right order. Move A towards B. 7 and 5 are in the wrong order, so we have to swap the data items so the 7 and the 5 cross over, and also the pointers swap positions. So the A goes to where the B was, the B goes to where the A was. And notice I've just labelled that I've performed a swap. We compare the B with the A, so the 5 and the 8 are in the right positions. Remember, we're only moving the A pointer in. The 5 and the 3 are in the wrong order, so we need to swap the data items. So the 3 and the 5 have swapped positions, and the pointers have swapped positions. We move A in. We compare the 6 and the 5. They are in the wrong positions. So we swap the data, 6 and 5. We swap our pointers. We move the A pointer in. Now this is where we come across a situation where both of our pointers are pointing to the same index position. This tells us that the 5 is in its correct sorted position within the array. This is known as a pivot. So now we're going to repeat the exact process that we did with the whole array with the two sublists. So we have a sublist 2, 1, 4, 3 and another sublist 6, 8, 7. So we establish our 2 pointers, A to the left, B to the right. Exactly the same on this side, A to the left, B to the right. For simplicity's sake, I'm just going to follow the sorting algorithm on the left hand side. The 2 and the 3 are compared, they are in the right position. Move the A in. The 1 and the 3 are in the right position. Move the A in towards the B. The 4 and the 3 are in the wrong positions. Swap the data, swap the pointers. Move the A in. So now we know that 3 is in the right position. So you'll notice that I am indicating the right positions of data using bolds and underlines. So the 3 is now in the right position. Let's look at the list to the right of the 5. The 6 and the 7 are in the right position. Move A towards B. The 8 and the 7 are in the wrong position. Swap the data, swap the pointers. Move A towards B. 7 is now in the right position. So we recursively call the sorting function. Now here we have a situation where A and B are pointing to the same index position. That tells us the 6 is in the right position, so we mark it accordingly. Exactly the same on this side. A and B are pointing to the same index position. That tells us the 8 is in the correct position. So quite quickly we've noticed all of these elements from 3 through 8 are in their correct index positions. So that only leaves us 2 elements which were to the left of the 3 to investigate. The 2 and the 1 are in the wrong position, so we swap the data, the 1 and the 2 positions swap over, the pointers swap over. We move A towards B, so the 1 is in the correct position now, and we mark it accordingly. That only leaves one item that was not sorted, so the A and the B are pointing to the same index position, so that tells us the 2 is now in its correct index position and have been marked accordingly. So now we can see the data is sorted using the quicksort algorithm. Finally, let's look at the big O notation of a quicksort algorithm. So the best and average cases are the logarithm of n, and that's due to its recursive nature of sorting sublists. The worst case scenario is n to the power of 2, and that would happen where pivot points are selected at the extreme lefts and the rights of the array. And the big O notation of the space notation is O to the n. So that means it will grow as the size of the data set grows. No additional data storage requirements outside of the array are needed. All of the data is being swapped internally within the array, so additional data storage requirements is not needed.